All right, let's redo this. I apologize if you looked at the previous video. I don't know, I've been having trouble with my recording volume on this one, so I don't know. I'm going to try to speak a little more clearly. And if I'm looking down, it's because I'm trying to speak where I think the microphone is. Because I'm going to redo a couple of these videos because the audio was so bad on the previous ones. First, we're going to talk about stress at a point. And really, since we haven't really talked about stress much, I mean, this really is an introduction to the notion of stress. You have some component to draw, kind of a bracket-looking thing. It looks a little structure, but you can see the products in there. So maybe it's loaded in one manner or another. You know, and as mentioned in class, we're primarily concerned about whether components fail, designing them so that they don't fail. We've looked at, for example, if you cut the body and expose the internal reaction forces, we've already discussed that. And we've been able to do sum of forces, sum of moments, to look at the equilibrating normal, shear, and moments. Now, these are what we're calling the internal reaction forces, and the, okay? Call this P. Now, the magnitude of those doesn't depend upon the size of the component at all, right? It depends only on the equilibrium conditions, right? So when we do sum of forces, it doesn't really matter how thick the component is at this junction, right? Now, obviously, have respect to the fact that as the part gets bigger, it's able to withstand greater loads. So there's a size effect to it, right? So these internal forces are not really good quantities to discuss whether the component will fail. You want something that's more at the material standpoint, and that's stress. So stress, we'll talk about two types: normal, which usually use the little Greek letter sigma, and then there's shear stress. Greek letter tau, lowercase letters, sigma and tau respectively. We'll talk about what's the difference between normal and shear stress in a second. Both of them have units of force per area, okay? So it's like these internal forces, but divided by the area, or otherwise normalized by the size. So they are intrinsic quantities. They're not dependent upon the size of the component. When you actually look at material strengths, the material strengths are given in terms of stresses. So you can say, at this stress level, this material, steel, will fail. So you can look at the failure with independent of the size. Okay? Okay. All right. So these, again, going back to the internal reaction forces, although they're quite easy to get from sum of forces and sum of moments, they really are arguably fictitious quantities. If you actually look at what goes on when we split the body, try to go a little bit bigger, this force P, okay? Now obviously what's going on this interface when we cut it is we're trying to represent the forces that this body is imposing on this side of the cut, all right? Now, those tend to be kind of complex in nature. They depend upon position. I'm trying to draw here. Now, if you think of it, if you zoom in at one point, it's very close to me. Blow it up. There's an exposed face. Have like a little bit of a, imagine we have some differential area here, right? There is a traction, distributed force on that surface, Okay, this is actually a traction. Each one of these points along the surface, the body on the right-hand side is exerting probably or arguably a different magnitude, direction, traction, force per area on this side of the body. Okay? This is like a distributed load. It's almost like a double. It's force per area. Okay? The total force we get is by integrating these internal tractions over the surface, and then we get N. Okay? This is a pretty complicated distribution, and it varies from point to point. It's a little more difficult to obtain this from the equation of equilibrium. Right? You actually need to have the elasticity equation. So in general, we're not interested in finding this attractions at point. Now, I probably should have mentioned it before, seconds ago. The attractions at the point, these really are the components of this stress. Okay. So again, if we look at it, imagine we have some differential area, okay? There is a differential force acting here. It's a vector. That differential force has a component in x direction, or normal direction, I should say, and in the plane. And for now, we'll just consider 2D stress, okay? So there's a normal component, and in plane component, or tangent component. This normal component is the normal stress. The normal stress at a point. So let's call this dF. Normal direction. dF. Direction. The normal stress is the limit. I've already written this in direction, but it's a limit as delta A goes to 0 of delta F normal over differential area. Okay? And so again, you can see that units of force per area, right? And then the shear stress is the limit. Same concept. But instead of looking at the normal component, we're looking at the tangent component. All right? So this stress, in 2D we have two parts, the normal and the shear components. Those are the projected components of these traction vectors, the internal traction force occurring in the body. So you can see it depends upon obviously the loading, the point we're talking about, but also the way that we cut the point. Force per area. These change their functions of position, right? That's the notion of stress. Again, two types. You look at it. Force here, there will be a normal stress component, also a shear stress component. All right. So the normal component you usually think of as pulling or extending the body. You have part tension or compression. Cut it here on this surface. This is what you would expect to see normal stress. Okay. Now these actually I've kind of drawn this incorrectly. These are balanced. But this were actually that's that type of modality. The shear stress is you have something like that. That tends to be a shearing type of phenomenon. Shear. Okay? So normal is the component normal to the plane, and the shear is the component in the plane. When we talked about 3D, you actually have two shear components on a three-dimensional surface. Cut face. You might have a vector here with a three-dimensional component. So this might have a component in this direction, and this direction. Okay? So this is the normal stress, and then you have two shear components. Okay? And they're different, they're actually different shear components. Okay? All right. Now, as I mentioned before, it's a little difficult from equilibrium conditions to get this precise stress distribution. It can be quite complicated. Fortunately, we do not completely interested in that stress distribution. And actually, let me pause it here. What I'll talk about next is average, normal, and shear stress. And that's probably, that is what we use most often.